Hey everyone, this is our second video for Chapter 2. Remember that in our last video we looked at the definitions of Bronsted-Lowry acids and bases. Remember that acids are proton donors and bases are proton acceptors. And we looked at some various acid-base reactions. We noticed that they all involved a proton transfer, and we could use arrows to show how the bonds are being formed and how they're being broken. We also reminded ourselves about the relationships, the equilibrium constants, the acid dissociation constants, and the relationship between acid strength and pKa, and the difference between pKa and pH. Remember that pKa is a constant for a given acid, whereas a pH is a property of a solution that can be changed just by varying the concentration of any acid. In this video, we're going to go on and look at how changes in chemical structure affect acid-base strength. So we'll see what it takes for an acid to be a strong acid versus a weak acid. In general, what we are going to most commonly do is look at the conjugate base of the acid, right? So if we label our components here, remember HA is some generic acid, and it's reacting with water to give hydronium ion and the conjugate base. Alright, so what we're going to be most often interested in is the relative stability of this conjugate base. Okay, because if we think about this acid-base reaction in terms of an equilibrium, we can draw a reaction coordinate diagram. Remember how we do these. This is energy on this side, and we would call this reaction progress. And remember, when we draw these, we have some energy for our reactant, right? So this would be our acid, and then we have an energy for a product. So here would be, say, the products over here. This would be H plus A minus, and we'd have some transition state in between those. Because this is an acid-base reaction, the direction of the equilibrium depends upon the relative energy difference between the reactants and the products. Right? So this distance here, remember, this would be the delta G, or the difference in free energy of the reactants and products. Right? If the products are lower in energy, like is shown here, remember that the delta G here would be negative, and this leads to an equilibrium constant which is greater than 1. Alright, so that means that in this case the reaction equilibrium lies towards the products. And that means that our acid, if we compare it up to this acid-base reaction here, then this equilibrium would lie to the right, and so this acid is dissociating, meaning that it's a strong acid. In contrast, if we have a reaction coordinate diagram that looks like this, so here's HA, and it goes to something like this. Here's H plus A minus up over its transition state like this. Notice that the difference in free energy for this reaction, delta G, would be positive because the product is higher in energy than the reactant. And so in this case, the K value would be less than 1, and this means that the equilibrium would lie back towards the reactants. So this would be for an example of a weak acid. So the equilibrium lies to the acid side, so it's not dissociating very much. So this would be for a weak acid. This would be for a strong acid. All right, so as the energy of the conjugate base here moves up or down, that's going to greatly influence the strength of the acid over here. So what we want to do is, again, look at the stability of the conjugate base. Right? These are the relationships. A strong acid will have a stable, which is weak in this case, conjugate base, a stable conjugate base. A weak acid will have an unstable conjugate base. We're going to look at 5 different criteria here. And in general, what we're going to do is that these are going to go in the order of decreasing priority. Okay, so if we're going to rank acids, we'll look at the top of this list and then on down. Okay, the first 2 of these are going to involve criteria that where the atom in A minus that holds the charge is different. Okay, so this is for different atoms for A. Okay, and then the last 3 here are going to be for examples where the atom that holds the charge is going to be the same. So these are going to be for the same atoms for A. All right? So let's look at some different acids, and we'll try to rationalize and understand their relative acidities. Okay, so the first group that we're going to look at are these compounds here. So we have methane, which is here, we have ammonia, we have water, and we have hydrofluoric acid. To compare the acidities of these 4 different compounds, what we want to do is consider the stabilities of their conjugate bases. So the first thing that we should do here is to draw out their conjugate bases. Remember that we always will generate a conjugate base by removing a proton. So we'll just draw these down this way. These are all in equilibrium. So if we remove a proton from methane, we get CH3. We have a non-bonding pair because the proton doesn't take any with it. And so this will have a minus charge. We have plus the H+. So there's the conjugate base. Let's do the same thing for ammonia. Now we're going to have NH2. Ammonia already has a non-bonding pair, so it will now have 2 non-bonding pairs. And like the conjugate base of methane, it will also have a minus charge. Each of these conjugate bases will have a minus charge. So here's water. We know already what the conjugate base for water is, right? So oxygen has 2 non-bonding pairs to start with. The conjugate base now has 3. This will have a minus charge. And an H+. What's OH minus? Yes, that's hydroxide. We know that one. Okay, and so then HF, hydrofluoric acid. Fluorine already has 3 pairs. So fluoride will have 4 pairs and a minus charge plus H+. Alright, so what we want to do is compare the relative stabilities of these 4 conjugate bases. So what property of these 4 conjugate bases is going to influence their stability? All right, notice that as we go from left to right, we have carbon, nitrogen, oxygen, fluorine, and each of those atoms is the one that's holding the minus charge. So what is it about those atoms which would influence their ability to hold the minus charge? All right, so the important thing here is the electronegativity. Okay, so the electronegativity of these atoms, is that going to increase going from left to right or increase right to left? Okay, so remember, electronegativity increases as we go to the right, and it increases as we go up as well. All right, so electronegativity is increasing going this way. Right? And a more electronegative atom is going to be better able to hold minus charge. All right, so our conjugate base stability should also increase from left to right, right? Because fluoride, being so electronegative, can best hold the minus charge, making it more stable. Okay, so how does that translate to acidity then? All right, so we said the strongest acids have the weakest, most stable conjugate bases, right? So that means that HF is the strongest acid here. So acidity is also going to increase from left to right. All right, and so let's compare, let's write out, we'll fit it in up here on the top, the pKa values for each of these compounds. Okay, so the pKa value of HF is 3.2. Okay, pKa of water, maybe you guys remember this one, 15.7. So notice that HF is much more acidic than water, right? Remember that each pKa unit represents a whole factor of 10, right? So water or HF is something more, over 11. 10 to the 11th times more than acidic than water. All right, so then ammonia has a pKa of 36, so that's getting very high. So that's a super weak acid, and methane actually has a pKa of something like 60. So remember that if it has a pKa of 60, it means that its Ka, its equilibrium constant, would be 10 to the minus 60th. All right, so is that a big number or a small number? Dang, that is a super small number. It means the equilibrium is way to the reactant side, and basically methane just does not dissociate in water at all. Super, super weak acid. All right, so the important thing here in this trend is our electronegativity. And this is going to be most important when we are looking at different atoms that are of the same size, or they're in the same row of the periodic table. We're going on the next one. Okay, so here's another group of acids. I have these all kind of written backwards from how we usually do, but we essentially have hydrofluoric acid on the right, hydrochloric, hydrobromic, and hydroiodic, right? We know these, especially HCl, HBr, right? We know these from Gen Chem. We know these are, most of these are very strong acids. All right, so just like what we did last time, is we want to consider the conjugate bases and consider the relative stabilities of those conjugate bases. Right? So let's draw our equilibria. So we're going to have I minus plus H plus. We're going to have Br minus plus H plus, Cl minus plus H plus, and F minus plus H plus. Alright, so just like before, what we want to do is consider the relative stabilities of these conjugate bases. Okay, so what is it that's going to influence their relative stabilities? Alright, so we might think, just like last time, that one very important factor here would be electronegativity. Right? So in this case, we're going up and down the periodic table, so which end of that, the top or the bottom, is more electronegative? So remember, as we go up, the electronegativity increases. So if we go this way, we have electronegativity. This is increasing. All right, so if we go based upon that, which end of this would be more acidic? So based upon this, predicted acidity, if we did this just like we did on the last slide, we would predict this to increase as we go from left to right. Alright, so now let's go back, let's look at the pKa values of these and see if we're right. Okay, so the pKa value of HI is minus 10. Alright, that means the Ka is 10 to the 10th. So now we have a very big number, meaning that this acid is going to completely dissociate in water, just like we know happens for all strong acids. Okay, HBr, the pKa is minus 9, right? Minus 7 for HCl. And for hydrofluoric acid, we already saw this. Look at 3.2. That is way less acidic. All right, so does this follow our predicted order? Okay, we're predicting that to the right would be more acidic. But look, HF has a much higher Ka, so this, in fact, is incorrect. And our acidity actually increases as we go this way. Increases. So why? Okay, it doesn't match what we predicted. So there's something else that's going on. I referred to it, or I kind of mentioned it in passing as we were at the end of the last slide. So the main other difference between these atoms is their size. So as we go down the periodic table, remember we keep adding another layer of electrons, and those electrons are getting further and further away from the nucleus. So it's increasing as we go down. Okay, so if we write it in here, we'll just have size, and our size is increasing as we go from right to left. Okay, so that means, right, I minus is bigger, but what does that matter? Okay, so that suggests, well, from what we have here, here's our acidity, right? Our acidity is increasing to the left. That means that HI must be the most stable, and it's also the biggest, so that means that the biggest anions are the most stable, okay? And that's true. So the key thing here is that a larger atom which is actually holding the minus charge, is more stable. If we think about this in terms of spreading out charge, so in general, the more we can spread a charge out, either over multiple atoms, or in this case, over a larger volume, just think about iodide being much bigger, and so that minus charge is diffused over a very large area, right? And diffusing the charge makes the anion more stable. Okay, so here the minus is spread over a larger area. Okay, so that makes iodide the most stable anion because it's the biggest one, and so then that makes Hi be the strongest acid. Alright, so for these two first trends, we looked both across the periodic table, right, going this way, and we saw that as we go to the right, we increase the electronegativity, and so the anion, the conjugate base, becomes more stable because a more electronegative anion can better hold the minus charge, right? So look at, here's our pKa's, 60, going to 36, 15.7, down to 3.2, all right? So that's going to be the trend whenever we're going across a row in the periodic table, all right? Now the other trend that we looked at was going up and down the periodic table. And remember, notice that we got a stronger acid as we went down because this is an increasing size. And with a larger atom holding the minus charge, that anion, that minus charge, is able to be more diffused and spread out, and that makes the anion more stable. All right, we can also see that same trend here between water and hydrogen sulfide, right? H2O and H2S. Notice that water has a pKa of 15.7. Hydrogen sulfide has a pKa of 7. So the same trend is taking place. Sulfur is a bigger atom than oxygen, so it can better hold a minus charge. All right, so we have two different criteria here that influences this already. So we have electronegativity, and we have size. All right, so we got three more to go. And in these three, the atom on A minus is the same. Okay, so we're going to look for different situations where we have the anion on oxygen or on carbon or something like that. In the top ones, it was always a different atom. Okay, so let's look at this example. All right, we already learned that methane had a pKa of 60. All right, so let's just say, well, let's go ahead. Let's do how we did last time. Let's go ahead and, for these three compounds, let's go and draw out their conjugate bases. All right, so all we have to do is remove a hydrogen. In each case, all of the hydrogens are the same, so we just have to pick one. All right, so I'm just going to pick the ones on the right side. So H plus will leave the pair of electrons. So we have this carbanion. Remember what the hybridization of this carbanion would be? Right, so this hybridization is sp3, and remember that carbon would be in a tetrahedral geometry with that non-bonding pair taking up the same kind of space as a bond would take. All right, what about the next one? Okay, this is ethene. All right, so we have this, and a non-bonding pair here, plus H plus. And then we have acetylene or ethyne to give us this. All right, so what is going to influence the acidities here? All right, so if we think back to some of the trends that we saw at the end of last chapter, what might influence the ability of these three compounds to give off a proton? All right, well, one thing that I might think about that seems like it would make sense would be the carbon-hydrogen bond strength. Right? It seems like to me that a stronger bond would be harder to break. Right? So can you remember which end has a stronger bond strength? So what's the important thing here? Right? So the important thing actually was this hybridization. So this is sp3, we already said. What's the hybridization over here? Okay, this is sp2, and these are going to be the same for the acids. And then this one is sp. All right, so remember back when we were talking about carbon-hydrogen bond strengths, that this bond strength actually increased from left to right. Remember, and our rationale was that when we have an sp hybridized carbon, it has a greater percentage of s character, and s orbital is closer to the nucleus, so that means that the sp hybridized orbital is holding the electrons closer to the nucleus, making a stronger, shorter bond. All right? So, if this is getting stronger going to the right, that seems like it would make acetylene be a weaker acid because that carbon-hydrogen bond would be harder to break. Right? So let's make a prediction then. You guys all agree with this? That means that acidity should increase going this way. Okay, so this is our prediction. All right, so what do you think? Let's see if this really is true. Okay, so like we did before, let's write the pKa's up here. Okay, so the pKa of ethane, which should be about the same as methane, is going to be about 60. So that's a super weak acid. Okay, ethene, all right, what do you think? Does it go even higher or lower? No, the pKa is 44. And when we go to ethyne or acetylene, it goes all the way down to 25, all the way. Still pretty high, right? So, which direction is the acidity increasing? Okay, the acidity is actually increasing as we go from left to right. So, I'm not doing very good on my predictions here, right? So, in reality, the acidity increases going this way. So why is this? All right, so the main trend here still remains hybridization, okay? But what we can do here is that we can relate hybridization to electronegativity, all right? So the argument goes like this. When we have an atom like this one here, that is sp hybridized, we'll use the same rationale we used when we talked about bond strength, right? Greater S character means that the orbital is closer to the nucleus, means that the electrons are held tighter, which can be translated to greater electronegativity. All right, so we can say that as we go from left to right, we're going to say greater percentage of S in the orbital leads to higher electronegativity. All right? And so just like we saw before, a more electronegative atom can better hold the minus charge, meaning that our conjugate base stability is going to increase as we go from left to right. Okay, so this end over here is more stable. Okay? All right, so this trend up here is basically hybridization, which then translates to electronegativity, which is something that we saw before. And we used electronegativity when we had the same atoms, or we're in the same row, and of course these are all carbons. All right, so hybridization plays a role here. Okay, so here's another example. All right, we've got two compounds we're going to compare this time. Notice, well, look at both of these. We notice that we have different types of hydrogens in these molecules, right? We have hydrogens that are bonded to carbon, and we have hydrogens that are bonded to oxygen. Right? So which of those two hydrogens are going to be more acidic? All right, so to predict that, or to understand that, we have to go back to the very first criteria that we looked at, right? And that's when we were looking at different atoms going across the periodic table. And so in that case, we saw that oxygen was more electronegative than carbon, and so the hydrogen on oxygen was more electronegative. So based upon that argument, we know that it's going to be the hydrogen in each of these on oxygen, which is the more acidic one. All right, so let's go ahead and draw out the conjugate bases. O minus and, okay, plus H plus. And over here, okay, so this is ethanol. This one we've already seen as well as acetic acid. All right, so let's draw out the conjugate base of acetic acid. And again, we're going to draw that by removing a hydrogen from the oxygen. Okay, so we're removing it as H plus. So to keep this balance, we're going to have a minus on the oxygen, right? We have 3 non-bonding pairs on each of these oxygens. Okay, so now what we have to do is consider the relative stability of these two conjugate bases. All right, but nothing we've looked at so far allows us to determine that, right? Because now, look, each one has an oxygen, the same atom. Basically, in these structures, it looks like they have the same hybridization. There's no difference in size, electronegativity. So how do we determine the difference in stability? Okay. So in this case, we kind of briefly mentioned this before, is that when we have this minus charge, these non-bonding electrons next to this pi bond, this is a situation where these electrons can move over here to form a new pi bond, and these pi electrons can move up on the oxygen, and we can draw another structure that's only different in the placement of the electrons. Okay, all the bonds are the same. Okay, this already had two pairs over here, and we have an O like this. Okay, so what was the relationship between these compounds? Okay, so this is a product of resonance. So this structure, the conjugate base of acetic acid, can have resonance. These electrons, we could say, are delocalized. But over here, on the conjugate base of ethanol, these electrons, because there's no pi bonds, so there's no pi bonds. So because there's no pi bonds, there's no resonance. We'll talk about resonance a lot more later on too, and so these electrons would be called localized. Localized versus delocalized, right? So delocalized means the electrons are spread out. So just like when we were looking at the size of atoms, when we have resonance, the minus charge, the electrons are spread, in this case, between more than one atom, and that helps make it more stable. Okay, so if we look at conjugate base stability, it's increasing as we go from left to right. All right, so which of these two should be more acidic? All right, so we would predict as well that acetic acid would be more acidic than ethanol. So let's look at the pKa's. Okay, so the pKa for acetic acid is 4.8, and the pKa for ethanol is 15.9. All right, so were we right this time? Yes, we finally got it right. Okay, so the presence or the ability of the anion to have resonance helps stabilize that conjugate base. All right, so we could also draw, let's draw resonance. When we have resonance, so we have two structures drawn here, but neither one of them are really the true structure. The true structure is going to be a hybrid of those two, right? So what that means is the minus charge, right? It's drawn on this atom for this resonance structure. It's drawn on this atom for this resonance structure. And so the real structure would have the charge spread between those two oxygens. Okay, so let's draw out what we could draw for what we might call the resonance hybrid. Remember, this would be sp2 hybridized, should be trigonal planar. Okay, so what I'm going to do is each one of these bonds has a double bond in one structure and a single bond in the other, so it's about 1.5 bonds. So I'm going to draw the other bond now as a dashed line, and a dashed line over here. And so we would have a minus 1/2 charge on one oxygen and a minus 1/2 charge on the other oxygen. All right, so less charge on each atom, that makes it more stable, and so this one over here, right, is more acidic because its conjugate base is more stable. Okay? All right. We want to write this in over here. So this one is for resonance. Shoot. Let me go back. All right. One more trend here. Okay, notice that each of these has the same functional group. That's going to be the acidic one. Okay, so here's acetic acid over here. Right, we already talked about it. Its conjugate base. Let's go ahead and draw out its conjugate base. Can have resonance. O minus plus H plus. Okay, what's the difference with this next one? Okay, so this next one has a chlorine on the carbon next to this functional group. All right, chloroacetic acid. So let's draw its conjugate base. Okay, so Cl. Okay. The next one, notice it's different because it has a fluorine on there. Let's draw its conjugate base. O minus plus H plus. And look at this one's trifluoroacetic acid. Let's draw this one. Okay, so what's going to be important here? Okay, so we looked at chlorine versus bromine before, right? When we looked at HCl versus HF, we were looking at size in that case. So is that what we should look at here? Well, not really, because notice that this minus charge in each case is on the same atom. So the size argument only works when the minus charge resides directly upon that atom. Okay, so in this case we have each of these, this functional group is called a carboxylic acid, and we have a carboxylic acid in each one. All right, so what's going to influence the stability of these conjugate bases then? Okay, the only difference is the presence of these halogens instead of hydrogen, like on acetic acid. Okay, so anybody think of a trend here? All right, well, if we're not sure, let's go ahead and write out their pKa's and see what the trend is, and then try to understand why we have that trend. Okay, so remember the pKa of acetic acid, I'm going to write them down here, was 4.8. Okay, if we have chloroacetic acid, it goes down to 2.8. And if we have fluoroacetic acid, it's 2.66. And when we have trifluoroacetic acid, it goes all the way down to 0.2. So that's getting to be a pretty strong acid. So as we add the halogens, it makes it a stronger acid. And as we add more electronegative halogens, it makes it an even stronger acid. And if we add even more of those halogens, it makes it an even stronger acid. Okay? So what does that mean about the relative order of stability of these conjugate bases? All right, so the conjugate base stability has to be increasing from left to right, right? Because this is the strongest acid over here. All right, so why is that the more stable conjugate base? Okay, so what happens in this case is that these halogens, being more electronegative, can actually pull electron density through the sigma bonds, through the single bond. So it pulls it this way, pulls it this way, pulls it this way, and the halogen is able to hold some of that minus charge. All right, so especially if we're over here, we have 3 of these fluorines pulling electron density out onto them, and that pulls some of this electron density away from the oxygen. So it's being able to share the minus charge, spread the minus charge out, but it's not spreading it through the pi bonds like we did in resonance. It's spreading it through the sigma bonds. Okay? And this is something that we call the inductive effect. Okay, and it involves spreading electrons through sigma bonds. Okay, so we see that as we go from left to right, it gets more acidic because of this inductive effect. All right, so I'm going to show you just one more example here. I'm going to add a new slide. Done for this video, but let's look at 3 more compounds. Okay, in this case I'm going to put, I just have a longer chain here. I'm going to put a bromine here. Remember how these skeletal structures work, right? So, oops, that's not what I wanted to do there. So, for example, so this carbon right here, how many hydrogens does that have on it? Well, it has 4 bonds already shown, so there's no hydrogens on this position, right? What about hydrogens on this carbon? Right, it has 1, 2, 3 bonds, so there would be 1 hydrogen here, 2 hydrogens on this one, 2 over here, and 3 on the end. Okay, so there's one of the acids. Okay, in this case I'm going to put the bromine over here, and then I'll draw one more. So notice they all have the same carbon skeleton. This one's going to have the bromine here. Alright, so the conjugate bases are going to look the same, basically, and let's draw one of them. Okay, I'm not going to draw them all out to save us a little time here. Like this, right? So, which of these 3 compounds? So, let's just say what's going to happen here. So, this is going to be another inductive effect, right? Alright, so it involves the more electronegative halogen pulling electron density through the sigma bonds, like this. And it pulls this charge away as well. Alright, so this is kind of similar to the situation we saw in the previous slide. Okay, notice that this bromine is farther away, and this one is in the middle, right? So if we look at acidity here, let's say relative acidity, this one is going to be the most acidic because the bromine is closest to where the charge is in the conjugate base. This one would be the second most acidic because it's next furthest away, and this one is going to be the weakest acid because those more electronegative atoms can just only pull electron density through so many sigma bonds. It drops off, this effect drops off as it gets farther and farther away. Okay, so the pKa's, just to see if these are consistent with the order that I just told you, we have 2.97, okay, 4.59, and 4.01, right? So, yep, those fit, right? So the most acidic has the bromine closest to the charge in the conjugate base. All right, so let's just summarize here. Okay, so the first things we looked at were electronegativity, right? Then we looked at size. Okay, in fact, I reversed these in our discussion because I thought it was easier to describe it that way, but really if we want to look at the order in which we should consider these, I'm going to put size on top, then electronegativity. And then we're going to look at hybridization, right, which remember was really an argue of electronegativity as well. And then we can look at resonance, and then inductive effect. So usually resonance effects are greater than inductive effects. Okay, so I'm going to write out some acids here, and we're going to predict their relative order. Okay, so HCl, CH3OH is methanol. All right, here's a carboxylic acid. Here's what's called an amine, and we're going to have a chloroacetic acid, or chlorocarboxylic acid. All right, so let's see if we can rank these. Okay, so what we're going to do first, we look at size. Okay, so we got to imagine the conjugate bases. I'm not going to draw those out. Okay, so let's look at what atoms are going to hold the charges in their conjugate bases. Here it's going to be chlorine, right, or chloride, oxygen, oxygen, nitrogen, oxygen. Okay, so based upon size, is there a difference? So chlorine, right, is the biggest, right? So if we look first at size, we would say that chlorine or chloride should be the most stable conjugate base. So you should predict that this is the strongest acid. And just from our chemical experience, Gen Chem, we know that hydrochloric acid is a super strong acid, and so that should be the strongest one here. All right, so we have chlorine, so that's the only one that has a different size, right? So the next thing we look at is electronegativity. So let's look at the other remaining four. So we have oxygen, oxygen, nitrogen, oxygen, right? So three of them are the same atom. One of them's different. One of them's nitrogen. So which is more electronegative, oxygen or nitrogen? Okay, so oxygen is more electronegative, so all of the species that have oxygen holding the anion in the conjugate base should be more stable, so those should be more acidic. So the one with the nitrogen, this amine, should be the least acidic. Right, so we have 5, so this should be last. Okay, so we did that. So next, we're going to look at hybridization. That doesn't really fit. We don't have any of the atoms that are going to hold the charge that have a minus charge on them, or that have different hybridization. But then let's look at resonance. Okay, so with the final 3 here, 2 of them should be able to have resonance, right? Both of the carboxylic acids should have resonance. Methanol has no resonance. Okay, so this would be 4. And then, so this is going to be, this one we picked based upon size. This one we picked based upon electronegativity. This one had no resonance. The last 2 have resonance, but which one's going to be more acidic? This one or this one? Okay, the chlorine is going to have the inductive effect, so that's going to make that more acidic, right? So that would be second, and this would be third. So this is second because of inductive. Okay, so we try, if we're going to rank these, we try to go through and pair them up based upon these different criteria. We can come up with our ranking. Okay, so here's just some practical pKa ranges to know. All right, so the most acidic group, so what we're doing here is kind of ranking them in some ranges. So here we have pKa less than 0. So that's going to be the most acidic, right? And notice that each of these species that has the lowest pKa, each one has a plus charge on the oxygen. So these all have a plus. Okay, so those are going to be the most acidic. Then we see a carboxylic acid has pK about 5. This has resonance. Ammonium ions are about 10. Alcohols and water, they're about the same, about 15. Remember, water was 15.7. And amines, remember, ammonia had a pK of 36, so these are around 36 to 40. Right? And then if we went all the way up to alkanes and things like that, we'll start with this and we'll get it bigger and bigger as we go. All right? So, one thing to notice, that if we have two species that are closely related, okay, for example, water and hydronium ion or protonated water, when we protonate them with a plus charge, they're going to be more acidic with a plus charge. Okay, so water goes to protonated water, or an alcohol goes to a protonated alcohol. The protonated alcohol is much more acidic. All right, we have ammonia, or let's do not ammonia. Let's pair these up correctly. Let's take the amine, and then we go to the protonated amine, or we have the carboxylic acid, and we have the protonated carboxylic acid. So in each of these cases, the neutral species is less acidic than the one with the plus charge. Okay, so I think that turned out to be kind of a long video here, but we've now gone through all of the different influences of chemical structure and how those influence relative acidity. All right, so we should be able to look like we did before at a group of acids and rank them based upon their acidity.